The natural logarithm has a really nice derivative. It's actually kind of remarkable, I think, if you think about it. The definition of the natural logarithm is not very nice. It's defined in terms of it's the inverse of the exponential function e to the x, which is defined in terms of this, super complicated looking transcendental number e. But the derivative of the natural logarithm of x is 1 divided by x. A very nice, very clean derivative. So, other than that, I guess this would be a pretty short video if I ended it here. So the natural log interacts, any function interacts with the chain rule. If you have the natural log of something, let's say x squared plus x plus 1, and you want its derivative, well, the natural log is going to be the outside function, and the thing inside the parentheses is the inside function. It's a very, very natural terminology here. And the derivative of this, well, the derivative of the natural log is 1 over x. So we take the derivative of the outside function, we stick the inside function into x. 1 over x squared plus x plus 1 times the derivative of the inside function, 2x plus 1, and we can perform that multiplication and get the derivative. Um, Sometimes people just memorize this. If we've got the natural log of a function and we want its derivative, it's always going to end up being a fraction that looks like this. The derivative up top, the original function down below. That's just what we got here. The derivative up top, the original function down below. You can memorize that or not. You can, just use the chain rule to get the same result. Connecting this to some previous material, the natural log of x is only defined when x is positive. So the derivative of the natural log of x, 1 over x, is also always positive because we have a positive number, 1, divided by a positive number, x. The second derivative is always negative. 1 is always positive, x squared is always positive, this fraction is always positive, but we have a negative sign in front of it. So the natural log is always increasing, but it's concave down. The rate it increases at diminishes as x gets big. And we could also, we could see that directly from the derivative as well. When x is 1, the natural log is increasing at a rate of 1. But when x is 100, the natural log is increasing at a rate of 1/100th. And when x is 1,000,000, the natural log is increasing at a rate of 1/1,000,000th. And so on. So the bigger x gets, the slower the natural log is growing. And as a result, the natural log ends up growing very slowly. So here's the graph of the natural log. When x is 1, it's growing at a rate of 1. It's not growing especially slowly here, but you see it slows down very quickly. When x is 10, it's growing at a rate of 1/10th. When x is 90, it's growing at a rate of 1/90th. When x is 1,000,000, it's growing at a rate of 1/1,000,000th. And the tangent line looks virtually horizontal. So this is it's actually something that people get wrong. People who do not study math will sometimes say that something is growing logarithmically when they're trying to say it's growing very fast, and that is the opposite of reality. Logarithmic growth is extremely slow, and it's extremely slow because of this derivative rule, that the derivative of the natural log of x is 1 divided by x.